with the presenters. So we have two main presentations. One by Professor Peter Wells, and the other will be shared between Cara Haag and Renato Manzoni. The format for today's event is we start with the first presentation by Peter, and then we have a short comfort break, followed by the second presentation. The final slot will be a Q&A session. To ask your questions, please use the Q&A icon and then enter your question. You can also vote for any of the questions appearing on the Q&A list. The questions will be ranked by the software, with those that have the highest vote being selected first. Now, without delay, I would like to invite our first speaker, Professor Peter Wells, who is the Director of the Centre for Automotive Industry Research at the Cardiff Business School, which is in Cardiff University. His talk will be on recycling of batteries. So over to you, Peter.
Thanks very much, Manu. I'll just call up my presentation here. Hi, everybody. Thank you for joining. It's a beautiful day here in Florianópolis, Brazil. It's the morning for me, but I guess for most of you it's the afternoon. Yeah, this is the joy of modern communications, of course. I think my role today is to perhaps provide some context for the more technical and engineering types of discussion that will probably predominate in this program, and to give a sense of the other kind of issues that might come to bear upon the future of battery electric vehicles generally, but also in terms of particularly battery packs and what happens to them, and where we're likely to develop an industry around the use and reuse of those packs. It's a very hot topic at the moment, as you're aware. There's a lot going on, and things have got kind of more complicated since the arrival of the pandemic. But what I'm going to try to do is take you through an overview of what I think are important issues other than the purely technical issues, and perhaps to raise a few things in your own minds that you can think about going forward from this point. I'd like to perhaps start by thanking Liana and the team for inviting me in. It's super nice of them. I've done quite a lot of work in this area one way and another, and this is the kind of things I want to discuss today. So I've got this idea of CASE, which is connected, autonomous, shared and electric cars, but also how that fits with concepts of the circular economy. And I'm going to think about scrappage rates. And what happens to cars at the end of their use tends to be rather a neglected topic. I mean, scrapyards in general, recycling centres in general, you know, they're not glamorous, they're not exciting, they're not the cutting edge, they're not seen as interesting really. But what happens there is going to be very, very important. And I think we need to think about that. I'm going to look at some short-term forecasts and then some long-term implications for electric cars, and then kind of come to some conclusions. Now, don't forget what Manu said. You can think of questions as we go along, type them up, send them in to him, and we'll kind of collate afterwards, and there'll be a big Q&A session at the end of all the presentations. So yeah, I would advise you to kind of, as things come to your mind, you know, by all means, send questions in. So then, this is my overall approach today. I'll skip through fairly quickly. I've currently got two big projects on the go. Actually, the STARS project on car sharing is just finished, and the ReLive project will run for another 12, 13 months. But these are two big funded programs. But of course, behind that, there's an awful lot of other work that goes on, research work with students, other projects, etc., etc. But also, I think the thing that I bring to these kind of discussions is the experience of a wide range of different types of research. So, you know, I've looked at the automotive industry from one end to the other, from literally going around steel factories and so forth, all the way through to visiting those recycling centres and so on. I've done it all over the world, from New Zealand to Iceland and everywhere in between. And I've looked at many aspects of industry. So that's looking at marketing, distribution, manufacturing, product positioning, research and development, materials use, consumer attitudes, regulation, behaviours. All of these are part of the kind of wide context within which the technical detail of battery design, electric vehicle design, and so on goes on. So that's what I'm kind of interested in. And I think it's important because I think we have to understand that cars are cultural objects. They fit into our societies in various ways, and those ways in which we accommodate with our cars, in which we build our lives around cars, these are important. They make a difference to design. They make a difference to the value of cars and their use. And as we've already seen, with the pandemic, behavioral changes, lifestyle changes can be very dramatic and very significant in affecting things like mobility. So, case, here we have it. The industry, I think around about 2016, people like Mercedes, Daimler started talking about this concept as a collective concept. Of connected, autonomous, shared, and electric vehicles. This was, if you like, an industry vision of where they thought they were going. And many other companies, not just Mercedes, have kind of more or less come on board with this, perhaps to different extents, with varying degrees of success. But it's a good organizing framework because it kind of summarizes what the totality of the industry is all about. And it's really restructured vast areas of this industry. We've got all sorts of people are suddenly becoming engaged with the automotive industry, and equally the automotive industry is suddenly becoming engaged with areas they never had to be involved with before. And of course, electricity is a great case in point. For many, many years, frankly, vehicle manufacturers didn't have to think about the electricity generation and distribution sector, apart from the fact that their factories tended to use a lot of it. But now we've got all of these new relationships, new products, new service concepts. It's all changing. As I mentioned at the top end there, COVID, I don't want to talk too much about this, but already the evidence is coming in about impacts on the automotive industry. Of course, the initial massive impact has been a huge drop in output, accompanying the huge drop in demand as dealerships closed and so on and so forth. But even beyond that, what happens next is massively uncertain. We don't even know what's going to happen with respect to the virus, but also there's a huge debate now going on. What are we going to do? Are we going to recover this industry as it currently existed, or are we going to take this opportunity to go in a different direction, to really push the kind of green mobility, the green agenda? And I think there's a lot of public support and quite a lot of political support behind that latter view, particularly across Europe, but maybe also even here in the UK. There's suddenly been an understanding that, yeah, we can change our lives in various ways. We can change how we travel. We can change our social behaviors and so on. And some of the things that are put in place, including events like this, including the way in which we in the university are likely to teach in the future, including conferences and all sorts of other aspects of life are changing. That will make a difference. It'll make a difference to many things in the industry, including how we go about electrification. So I tend to work with this kind of little world, so to speak, to understand case that it's a totalizing vision. So it's not just about new cars. You've got new production systems coming through. You've got different ways of owning and using cars, a huge raft of new materials and components. It's all going on there. This is a whole new world being created by the automotive industry. And I think that's important to understand because people think of this industry sometimes as being old, as being somehow rooted in the past. But I think what this tells us, and what recent history has told us, is that those kind of fantastic up-and-coming tech giants and so forth, they can't do the complex task of product integration that defines the modern car. And all of these new areas are part of that process. So, Case, pretty well understood, but I've been asking myself a bit, well, how does that fit to the circular economy? And of course, that's really kind of relevant once you start thinking about battery recycling. I think within the industry, there's basically an assumption that life carries on, business as usual will be fine, and that we can kind of make some form of transition into the circular economy in a relatively untroubled way. But I'm not entirely sure if that's going to be the case. So here's a kind of nice little schematic just to say, okay, so we wrap the case concept into the circular economy concept, and life carries on. But if you think about how this fits against things like the waste hierarchy, you can begin to see some of the tensions and some of the problems. So the green economy, this has been around a while. I mean, essentially the idea of green growth came out of the last financial crisis around 2008, 2009. And people like the European Commission were offering these kind of visions that said, yes, we can have economic growth without increasing the consumption of resources. And we can actually, at the same time, reduce the impact on the environment. So this is the vision into which CASE and the circular economy goes on. But if you look at the original kind of waste hierarchy type diagrams, what we see is that the first step in this is prevention. In other words, probably not having things rather than having things at all. But then look at how the circular economy is supposed to work. You have raw materials coming in, you go to manufacture, distribution, use, disposal, and then they all start cycling around. So this is all very well, but in the context of something like battery electric cars, you need to create enough product going in order to drive that circle. But the circle itself is getting bigger and bigger as you sell more and more electric cars. So net material consumption, particularly of key materials such as cobalt or lithium, that net material consumption will go up, and will go up by quite a lot. At the moment, we don't know quite how big that circle needs to be as far as it applies to batteries. So then you can ask yourself some fundamental questions. I mean, you know, do we have to actually simply produce fewer cars? So far, the evidence is pretty clear that nobody has really achieved further economic growth without growth in material consumption. In other words, that the idea of resource extraction driving economic growth continues to be pretty well established, and it's hard to break from that. It's even hard to break the carbon emissions from economic growth. Even in places which have a high amount of renewable energy, it's still proving very, very resilient, this relationship between economic growth and material consumption. So you know, we have to focus first and foremost probably on reducing or preventing the use of materials in the future. And you know, maybe that means more efficient use of materials, so fewer materials per vehicle, so to speak, in our case, or maybe smaller cars, and probably a stronger focus, therefore, on some of the things that we already do to reuse and re-engineer vehicles. I'm going to come back to some of these points as we go through the longer term implications further in the presentation. Here's some pictures. Yeah, these cars are as old as I am, which is slightly worrying because they look a bit better. So clearly, these are cars from Cuba. So as you're well aware, you know, Cuba now is famous for these beautiful old late 1950s American cars. And they're lovely. Look at them. Yeah, they're beautiful things. So in the late 1950s, 1957, I think it was, America kind of cut Cuba off economically, and imports of vehicles stopped, and the Cuban economy became strongly isolated. What's the consequence of that? Well, the consequence of that is these cars are still in use. And although I'm not a great fan of Jeremy Clarkson, I once saw a program of his in which he visited Cuba, and he demonstrated or showed what they did to keep these cars on the road. So you can take, for example, the bonnet of this rather lovely red one on the left. They would get something like an old washing machine, or maybe a garage door or something like that, a metal. They would bash it out by hand, smooth it, spray it, put it on. Slightly more worrying was the way in which they made brake fluid using sugarcane juice. But moving on from that point, the thing is that these very lovely vehicles demonstrate a very important point, that almost any car, in theory, can be kept on the road. So when we think about scrappage and the scrappage of vehicles, the assumptions that we make are actually underpinned by economic and technological situations rather than some immutable law. There is, of course, deterioration over time. And every now and again, cars are involved in crashes, and those crashes may be so substantial as to require the vehicle to be written off. But actually what's underneath that are things like depreciation rates, and whether it costs more to just keep a car or retain it, or replace it rather. So the calculus of that depends upon many other factors. It depends upon the wealth of individuals or the community. It depends upon regulatory factors. Are older vehicles kind of driven off the road by regulatory intervention, etc., etc. It's not clear at the moment quite how electric vehicles will fit into some of these issues. They take a very simple example. At the moment, I'm the proud owner of a slightly ancient Nissan Leaf. Its insurance is higher than my previous BMW 3 Series. Now, I kind of think to myself, why is that? The Nissan Leaf, fine vehicle though it is hardly in the same performance league as my BMW 3 Series. But talking to insurance people about this, they have two major concerns. First, the vehicle itself is kind of expensive to repair. So if you do have a crash, it's going to be tricky to repair it. But also, second, these vehicles are heavy for their size, and weight matters to the insurance industry, because the more mass you carry into a crash, the more damage you're likely to cause. So scrappage rates are actually pretty complex and pretty confusing. Now, in the kind of recovery period after the last financial crisis, 2008-9, one of the things that happened almost universally across Europe were these scrappage incentive schemes. And the deal is fairly clear. You have an old car, maybe say 10 years old, and actually some of the schemes even went as far as 8 years old. You take that car into a dealership, you buy a new car, the dealership has to verify that the old car is then scrapped. And thereby, of course, the age of the park is reduced. The industry generates a lot more cash. And funnily enough, it was actually even a bonus for the government in many cases, because the VAT on the new cars would cover the scrappage costs, incentive costs on the old cars. Now, I think already we can see that this time, with schemes being put forward to try to revive economies and the automotive industry post-COVID, we can see that the picture has changed a bit. There's much, in most cases, a much stronger green agenda being pursued. Most obviously and most strongly the French have done this. Interestingly, also a much more nationalistic solution. They're talking about trying to support French industry and French car companies and so forth. So in some ways, the pandemic has had the effect of slicing up a bit the unity of the European Union. But they've got some clear targets, they've got some clear help, and it's interesting to see that they've understood that to date at least, subsidies for electric cars have tended to go to the rich rather than spread across society. So they've looked at this idea of even converting old cars from petrol and diesel into electric. I think this is very interesting because actually they've got a number of companies in France that are quite big in this area now. They've recognized that and are supporting them. And it seems to me that this is likely to be something that will increase with time. This is not just with actual petrol diesel, but actually also with electric cars currently in circulation, which might want to be put through some sort of battery replacement process in the future. So this is a sign of things to come in a way, and I think very interesting, and probably going to shape the market in important ways. Of course, here in the UK, it's different. Most of the cars sold here, I say most, typically more than 90% of cars sold here are imported. And now we don't have that shared destiny, so to speak, with the European Union. Is the support for some sort of scrappage scheme from the government, at least, has not been so strong. So what's happened over time, over a long period of time, really, is that the stock of cars has gone up. In other words, new registrations have been higher than the rate of old cars being taken off the market. And there are ups and downs in the peaks and the scrappage incentive schemes and so forth. And of course, that means that in principle, at least, vehicle longevity has gone up, at least in terms of the data available over the last 30 or 40 years. But it's immensely variable. And this, just to kind of think through one tiny example for you, go back to the case concept and let's look at autonomous vehicles. What impact would autonomous vehicles have on scrappage rates? And I've kind of written a few questions here to suggest that it could go all sorts of different ways. And until we get to see some experience of this and get to have some data around this, it's hard to say a priori that there will necessarily be one impact or another. I'm tending towards the view that, well, first, it's going to take a long time to get fully autonomous vehicles. Secondly, in principle, autonomous vehicles plus electric should mean greater longevity. Firstly, through reduced crashes, so good. But secondly, because there should be a much more optimized use of the vehicles, and it should be possible to retrofit and so forth. And if you have that, then it becomes a much bigger social question. How many vehicles do we want on our roads? It's already the case that, apart from the actual driving problem, parking anywhere is a bit of a nightmare. So I think many of these issues will cause problems elsewhere. And I think that's going to be a big issue to cover. Looking at the UK, average age of cars in use, 6.8 years in 2003, 7.8 years in 2015. Average age when a car was scrapped, just short of 14 years in 2015. Of course, the cycles of economic life and so forth have a big impact on this. When a recession hits, what happens? Well, new car sales fall, but also retention periods go up. In other words, people hold on to their cars for longer. One thing to flag, though, is that the data, especially around what's happened to the kind of old cars in use, the data is very weak. I was quite surprised, I've got to be honest. I was quite surprised once we started doing the research for the battery project to find out there was a lot of leakage in the numbers. Across Europe, this is true. I mean, actually, the UK has one of the better systems in place for keeping track of what happens to old cars. But across Europe, there are literally millions of cars disappearing every year. Your guess is as good as mine as to where they might end up. A lot of them apparently go either to Africa or Eastern Europe or get broken up into parts, but it's very, very hard to say. And again, just look at the data from Europe with ASEA, you can see some very variable figures. So a country like Poland, relatively small fleet of cars, relatively economically still developing. So average age of cars much, much higher. This is a picture, quite like this. This is a picture taken just around the corner from my house in Penarth, in one of the back lanes there. And what it shows you is something which is very, very common in Britain, which is to say cars parked up. These are projects, most of them, as in this case, abandoned projects. There must be, I don't know, millions across the UK of cars like this. And there's a system, of course, in the UK to deal with it, and it's called SoN, the Statutory Off-Road Notice. Now, I want to show you this for a couple of interesting points. I mean, the first thing is, looking down the percentage of total registered as SoN, look at the Ford Escort. 58%. So these are original Ford Escorts. So Mark 1 Ford Escort, Mark 2, and so on, before Focus, before any other products. So these are primarily pretty old cars, but an awful lot of them still registered at least through the SON system. So that means that there's a huge enthusiast base around the Ford Escort. And you can see it, you know, if you go to those kind of motoring events that my friend and former colleague Paul Neuenhuis used to love going to, and probably still does, you see these people gathering together to look at their Ford Escorts or their DAFs in his case, or whatever it may be. Now, this is another important thing about the longevity and the use of cars and so on. That there's a relatively large number of these cars registered as statutory and off-road. That means that once you go into a battery electric world, you'll see the same. There will be people storing and hoarding their cars for a long period of time beyond their apparent use. Anyway, so what's going to happen over the next 5 or 10 years? I had initially anticipated a greater rate of scrapping. I'm not sure if that's the case anymore because of COVID, but I'm expecting the data to be better. But I think there's one big issue that we need to focus on, and that's the potential early scrapping of electric vehicles that were produced in the first wave or two of this renewed industry. Right now, EVs are becoming much more kind of materially intensive. I did a little calculation here just for fun. You know, there's a huge lot of materials in here. So what's gone on really is that the automotive market and the manufacturers have pushed heavily into SUVs or those kind of crossover vehicles like the Qashqai. That's been a great big growth area, and it's good for electric in a way because they're big enough to take a big battery pack. You know, think of something like the Jaguar I-Pace. So that's great in many ways, but in a material sense, this is desperately inefficient. So you have something like the Tesla, basically 2,200 kilos thereabouts. It's a good way of moving batteries around the country. It's not much good for anything else. Interesting enough, the Tesla came out as the worst in the latest JD Power Quality Survey in the US. So there we go. So you get vehicles like this, big, expensive, impressive performance in many ways. So they're quick, they're getting longer and longer range, but is that really the way we're going to go in the future? We've got people like Volkswagen busy building vehicles in a more kind of toolkit way. I think this is much more interesting because what this shows you is that the industry has migrated from a very, very simple sort of so-called platform and hat strategy of the past into this way of thinking about the architecture of the vehicle as a kind of three-dimensional jigsaw. What that tells me is that although the industry is heavily into SUVs at the moment, and that's what they can sell, other configurations are more possible. And we see that in the new MEB matrix concept for Volkswagen for their battery electric vehicles. So this concept, they're essentially saying, look, you can build almost anything around this. And indeed, they can offer it to other vehicle manufacturers as a sort of package to take away, which of course will help them get some volume. But it's a very flexible, very interesting way of thinking about the design of the vehicles. All of a sudden, you know, you don't need to have a big air intake at the front to cool the big petrol or diesel engine, etc., etc. So the design potential out of these new vehicles will get much, much bigger. But then, you know, here I am. I've got my Nissan Leaf. It's 4 years old now, and I'm coming up to 5 years old. The battery pack warranty is 8 years. The car ought to be able to last as long as any other. In other words, should on average last around 15 years at least. So what am I going to do then? Because with a typical petrol or diesel car, it didn't really matter if the warranty on the engine expired because you could repair it, you could replace it. But I'm not sure what's going to happen now. Is is going to be a challenge, shall we say, at least. So what's going on here then? You've got some cars that are in need of probably some sort of replacement battery, well ahead of the typical normal end of lifetime for the vehicle as a whole. Meanwhile, new electric cars are getting cheaper and cheaper. The technology is getting much better. There's been rapid fall in pack costs. There's nothing around in terms of second life at the moment for me to sell my car battery onto. All of those subsidies are for new cars, not for old. So we've got this kind of classic perfect storm, really. It's leading me and many people now to ask themselves, would you buy an out-of-warranty battery electric vehicle? Now, you can get third-party warranty extensions, I've seen one for Renato, it takes you from 8 years to 10 years, for example. But why would you want to replace the battery pack? Why would you spend, let's say, £3,000 replacing your battery pack on a vehicle that's worth perhaps £5,000 in total? So this is leading us to think that there might be a really strong wave of spiraling depreciation, resulting in a peak in premature scrappage of BEVs in the short term. So we start to sit down and try to think about this in a bit more coherent way. So first of all, if you want to forecast the rate of BLV arrivals, then you've got to think about how many battery electric cars you're going to sell in the first place. Now, what's the share of BEVs going to be? Then you've got to forecast the longevity of those packs separately from the cars, because they are possible to separate. And so we adopted this idea of the obsolete lithium battery stockpile. So it's a slightly kind of strange concept in a way, but it basically tries to combine out of warranty batteries that are still on the vehicle with scrap vehicles. So to get to that point, we have to forecast the rate of industry insurance write-offs. We have to add in replacement under warranty and think about what happens to batteries beyond the warranty period. So our forecast for registrations, we took kind of 3 scenarios that look a bit like this. Now, obviously, since the pandemic hit, the numbers were all over the place. Just before the pandemic hit, at the end of 2019, battery electric vehicle sales were really doing well, really rocking along. A lot of new product coming into the market, a lot of stronger consumer acceptance, a lot of charge points being built. Things were going really well for this sector. And so actually we were pretty near to the top curve there, the 24% growth curve. So things are going great, but now, of course, don't know. The share of electric did very well in the crisis, and has continued to do well, not just in this market, but in many others. So in that broad sense, the shares do very well, but of course the absolute numbers are much, much lower. So then we try to forecast the stockpile of batteries, which is to say, those batteries which are being scrapped or liable to be scrapped at a given point in time. Of course, the peak is further forward than the growth in the electric vehicle sales. And we've kind of got these nice smooth curves generated because, that's what people expect to see. But my question is this really, by the time we hit 2024, 2025, are we going to see a lot of these older battery electric vehicles near the end of their battery life coming into scrappage simply because nobody wants to buy them? It's entirely possible that you'll have a vehicle that's just fundamentally sound, it's in good shape, there's nothing wrong with it, it's just this battery is expired and nobody wants to buy it, and it's not worth replacing the battery. So we started thinking about that as well, thinking about how we do the kind of management of all of this, and what's going to happen around the kind of regulatory issues and so on, but also what happens, going back to our big picture, to the positioning of the industry around things like material stewardship and so forth. And in the longer term, I think all things are up for grabs. And there could be fewer vehicles, it could be more refresh, it could be a shift from being a primary consumer of raw materials to being custodian materials. So I put together 3 little kind of vignettes to consider this by. first of all, the sub-car sector, that's less than a car. There's a lot of interest in this because, you know, in terms of pure eco-efficiency, this is much, much better. There's so many things that are good about this solution. Now, you've seen a lot of these around Europe. They're quite popular. Various versions of this are popular in Asia and China, places like that. The US, not at all. But certainly in other markets, I think this is going to be a big, big growth area. And in efficiency terms, you can see from this diagram that the very, very small vehicles are leaps and bounds ahead of things like the S or even the Nissan Leaf. And there's lots of things that come under this umbrella. We see them on our streets almost daily now. I love these little electric unicycles. They're fitted with gyroscopes to help on the stabilization. And I've seen them in use in the UK, elsewhere. They're very popular. These hoverboards, they got a bit of a bad reputation for ignition, which gives you some idea of the hazards of lithium-ion batteries. But again, with time, one of the things that all of this demonstrates is that battery electric is a very flexible way of doing mobility. My second kind of type, so to speak, is the drone. So under this vision, you get basically utilitarian mobility. Lots of vehicles, all the same, running around, little blobs, doing on-demand pay-per-use in very, very functional, utilitarian way. So they'll probably last for a long time. They'll be relatively low cost to produce and use. There'll be a high amount of refurbishment because they're not going to be individually owned. These are shared vehicles. They're going to run around city centres doing mobility for us. And they're going to look like this. Well, actually, they're not, but you get the idea. Actually, Airbus has pulled out of their relationship with Audi on their project. They couldn't make it work financially. Continental are, of course, a supplier, and they were just using this as a showcase for their technology. But it gives you an idea of kind of where the industry likes to think it might go. But these kind of amorphous blobs running around, picking people up, dropping people off, no drivers involved. This is one vision of the future. The alternative, or perhaps not say alternative, I think these things may run in parallel, is the fortress. And you see a lot of this idea that the vehicle is a dynamic sanctuary to provide you with comfort and security. This is the Mercedes 015 concept a couple of years ago. It's a luxurious interior. There's some cool dudes doing some officey type things. It's giving you the impression of almost being inside your private jet. This is the Peugeot Instinct, same sort of idea, lots of interesting kind of design features and style features. It's very much about luxury and protection. And you can see that basically, the way that these companies are trying to position themselves is say, well, look, we can secure you from the uncertainties of the world outside. So in this world, these are expensive vehicles, of course, but they may end up like the Rolls-Royce. They could end up being these fantastically long-lived vehicles with a very high rate of retrofit, very reduced rates of total recycling. The only things you're recycling are the bits that wear out. Maybe the battery packs will be one of them. But then the vehicle becomes something of almost something you hand on to your children or your, as an heirloom to other people. And this is an example of how it works. These were the days when Jaguar actually had some money. And you'll see, I actually saw this vehicle a couple of years ago in London at an event that Jaguar hosted. And it's beautiful. Oh gosh, these are collector's items anyway. And I'm sure some purists were appalled at the idea that you should install an electric powertrain into this device. But it was a showcase, and it was there to show that it could be done. And it could be done without any significant impact on the look or the feel of the car. Of course, the drive changes, probably for the better, but it just shows you that this whole world could exist. So I can see that there are different sorts of automobility might emerge out of this future. And that means that there are different sorts of future for battery design and so forth. Now, I haven't touched on the question of different battery chemistries, different battery forms, and so on. I would say that in the regulators' world, the ideal is, of course, commonality. You know, if every car battery was like your AAA battery, so you could stick inside a flashlight, or a standardized phone battery, you know, if they were all like that, then life would be easy. But this is the classic problem with technological change. On the one hand, you've got all of this innovation going on, and you'll see presentations around that in this whole series of lectures. But you know, all this innovation makes things better. It makes things faster. It makes things more durable. It makes things cheaper. That's what innovation is all about. But in order to achieve that, you fragment the market and you create the obsolescence of the previous generations. We've seen that already happening in things like phones, is, I believe, happening in things like battery electric cars, and will continue to happen going forward into the future. So what do we conclude? I'm wondering whether vehicle manufacturers will want to hold on to their batteries. I noticed, for example, VW's done some interesting things. You know, they've got their setting up their battery manufacturing, fine. They've got their platform, great. They've got a whole kind of product range outlined. Of course, they had the emissions scandal in America, which kind of prompted a lot of this. But they've done some other interesting things. Two I'd like to highlight. One, they've set up their own battery recycling facility, so not putting it out to a third party. The second is slightly more subtle. They have gone to an agency model for selling their electric cars in Germany. Now, that's different to the franchise dealer model. And what the agency model does is allows them, Volkswagen, to retain ownership of the vehicle and the battery pack. Because all the financing and everything is in their hands. So I think that this move to an agency model is part of their overall strategy to secure future material supply by retaining ownership as far as possible. And that means that the circular economy loop that I discussed at the top end of this is going to be internalized by Volkswagen within their own business. I can't see everybody going that way, but that's certainly going to be their solution as far as they can tell in the future. My other main conclusion is that the future will be massively more fragmented and complex, but we have a paper that sort of summarizes at least our view for 2025, 2026, and so forth, which is this one here. And I will leave you with those thoughts and hand you back over to Manu.
Okay, thank you very much, Peter, for this excellent overview on battery recycling and the impact of such technology on EVs and the future of electric cars in general. For those who joined late, we said at the beginning that if you would like to ask questions, please use the Q&A icon, which is at the bottom of your screen, or maybe at the top, depending where you're watching, and ask your question, or you can vote for the questions that have been asked already. We will take all the questions at the end after the second presentation, and the software will prioritize these questions according to how many votes they have. If not, we'll ask just in the order they come in. We now have a short comfort break so to make coffee or go ahead for a little bit of a walk. And we return at 3 p.m., which is in 15 minutes. So I'll see you in 15 minutes for the second presentation. Thank you very much. Okay, so it's 3 o'clock and we're ready to start again with the second presentation. So welcome back to the presentations. So the second presentation is from FZSoNick SA, and the presentation will be shared between two employees of the company, Cara Haag, who is the general manager and board member, and her colleague Renato Manzoni, who is the product and application manager. This presentation will introduce salt nickel batteries that are made by the company. So over to you, Sarah.
Okay, great. Thank you for the introduction. My name is Cara Haag. I'm the general manager for FZSoNick in the US. We really appreciate the team for inviting us to speak today about our battery technology and the role of batteries in decarbonization throughout the infrastructure and the network of EVs all the way back to the grid. What I'm going to do is spend a few minutes just talking about the company and where we came from. A lot of you may not have heard of this sodium-nickel-chloride battery. That's because we don't do a really great job of marketing it, but we have had a lot of success in the market, especially when customers learn about the technology. So with that, I'm just going to go through and spend some time talking about who we are, where our footprint is, and then I'm going to hand it over to Renato so that Renato can focus on the more important technical part of the chemistry, the battery, and then the applications. So with that, Renato, if you can go to the next slide.
I can.
Okay, so we started from a company that was called Electra 1938. In 1938, the Dolcetto family in Italy created a three-wheeled electric vehicle. You may not be familiar with the Electra 1938 name, but probably if most of you are in Europe, you're familiar with the FIAM name. In 1942, they changed their name to FIAM and started focusing not only on the three-wheeled vehicle, but producing components for vehicles that were made of lead-acid batteries, and that became the main focus of the company from 1960 to 1990. They became a worldwide leader in both the automotive sectors and then the industrial lead-acid batteries and components. We started looking as a company in the late 90s, well, actually in the 2000s, at other alternative chemistries. We looked at things like fuel cells, lithium-ion batteries, and then salt-nickel batteries to see what other type of battery chemistry or alternative chemistry or product we could bring in-house to go along with lead acid. They decided after a lot of investigation to create a JV with a company called Mestia on the salt-nickel battery. Mestia has been producing the battery commercially since 2000 for electric vehicles with the sodium-nickel-chloride battery, which we now call SONick. It originally was designed as a Zebra battery, if you're familiar with that. We had the JV to create a battery for the telecom market, which is energy standby. And in 2011, unfortunately, the CEO of Mestia passed away. We had the opportunity to buy 100% of the company. And so we bought all of the manufacturing and the facilities associated with Mestia for the salt-nickel battery and brought it in-house. We have another part of our history, which is with the lead acid portion of the business, there was a JV that occurred with Hitachi, where Hitachi owned 51% of all of the lead acid business, and Electra or FIAM owned 49% of the business. So all of the branding with the FIAM name went over to Hitachi with that joint venture, and then all of the companies underneath rebranded with different names. And that's how FZSoNick became its own individual corporation underneath Electra 1938 Group. And so with that, the FIAM Group name changed back to Electra 1938. Okay, next slide. So this is an overview of the structure of our company. The group at the top is the same as it was under FIAM Group. We have different businesses that fall into that. You can see how the traditional lead acid FEOM business is owned 49% by the company and 51% is owned by Hitachi. However, Hitachi did sell this off to Showa Deca. So now all of the chemical business is now under the name Showa Deca to make it even more confusing. We have FZSoNick Italy, which is the headquarters of our Sodium-Nickel-Chloride business. And then we also have a group of companies called FZSpa, which does horns and antennas for the automotive industry. So they are providing the horns for about 90% of the OEMs across the world. Okay, so next slide. If you look at the footprint of our sodium-nickel-chloride business, we only manufacture the cells in our Stabio, Switzerland location. So the process is very complex. It's a ceramic cell inside a stainless steel tube. Renato will go into a lot more detail in that. So we make the cells in Stabio, and then the battery assembly is done there. And then for us, where I'm in Atlanta, Georgia, but our headquarters in the US is in Elgin, which is outside Chicago. So our US headquarters is in Elgin, Illinois. We bring the batteries in as a module to that facility, and we do firewall testing, which is just taking a sample size lot of the batteries and running it through a warm-up, charge, and discharge cycle to ensure continuity of quality. And then we also do configuration for our customers in the US on the batteries, package it together with any accessories they might need. And so some of the things that we can do, Renato will get into this, but we can do, we can change the recharge current and make the battery a little bit more personal for the customer. But also we have a repair and service facility in Chicago. One of the unique things about this technology is that it is repairable. So outside of a warranty, if the battery breaks, you can actually repair the battery. So when Peter was talking about a circular economy, a battery like this that you can actually repair and either replace a cell or a battery management system will help create that circular process to keep the batteries in the market much longer. And that is one of the unique things about this chemistry over any other battery technology out there. We have our headquarters in Montecchio, Italy, which is in Vicenza, in that region. We have just started doing assembly in Wuhan, China. So one of the things is that we do not sell our cells to any other customer to create their own batteries. We're the only manufacturer of our cells for this product. So it's a little bit different than something like lithium ion, where anybody can go and buy a cell from LG or Hitachi and build their own batteries. So we can control the market a bit that way. We do have a assembly plant in Wuhan, China, where we're getting the cells from Switzerland. We're bringing them to that facility in China and assembling the batteries there. Those batteries are only going into the Asian market for customers we have there for rail, energy storage, etc. But some of the benefits of being able to do that and do the assembly in the local markets is being able to source the materials locally in that region and save costs on shipping. In the US, we aren't doing the assembly yet, but it is something that's in our long-term plan as we continue to grow. And then you can see that we have service facilities also throughout the world. We have one in Brazil, Malaysia, and the Philippines. Okay, next slide. This is an overview of our group revenues in 2019. We did 630 million euros. Usually I have to convert this to dollars when I'm doing the presentation, but obviously most of you are probably from Europe, so that's very familiar for you. As far as the portion of revenue of the group, the Sonic revenue was 30 million euros of that. We did have 25% growth from 2018 to 2019, and we were also able to increase our EBITDA by 10%. So those are all really great numbers for our company. We've had a lot of good growth, and we're able to increase our margins as well. So as far as our markets that we focus on, you can see in the slide on the left that the majority of our sales and revenues right now is coming from energy backup. The energy backup applications vary from telecom, so some of our large customers include T-Mobile, AT&T, CenturyLink in the US, Globe, and some other telecoms in Europe. We also have 20% of our revenues coming from the mobility market. We have electric buses with Iveco, with Irizar, sorry, and then delivery vehicles with Iveco, and also some mobility applications like Google Bus in the US. And then there's a smaller portion of the business that's coming from energy storage. Globally, most of this is outside of the US. There's starting to be more of a trend for energy storage systems in the US, as well as it has been in other areas of the world. And we have batteries that are in applications ranging anywhere from residential energy storage, so smaller systems, all the way up to large grid scale energy storage systems with megawatt hours to support wind and solar and some renewable energy generation to make it more stable. In 2019, we produced 2,000 cells per day. That was equivalent to 4,800 pieces of battery. Okay, next slide. This is an overview of where we have our products deployed by application. So as you can see, when we created the JV with Mestia, we were focused really mainly on the telecom market, and that's where we started. We started deploying batteries in telecom in 2011, and between 2011 and the present time, 2020, we have over 20,000 battery systems installed. We just started targeting oil and gas. We have had success with Exxon. We have batteries in Petronas. A lot of the oil and gas industry is very interested in the battery because of safety. So as Renato will get into, the battery is very energy dense. So we compete a lot with lithium for energy density. But one of the main things that we have realized as part of our value proposition is that the chemistry is extremely safe. There's no issues with it catching on fire, exploding, or having any sort of adverse event in the field. And in some systems, that's extremely important, especially even in electric vehicles. I mean, we all know that the internal combustion engine vehicles can catch on fire, but those are usually older vehicles, and we have seen some of the newer EV vehicles catch on fire as well, but those are new cars. We need to make sure that safety is always being addressed. We have installations across the globe in 5 continents, and we also are focused on railways. So you'll see our batteries in railways, mainly for energy backup. So they'll hang underneath the train for monorail applications. It's an auxiliary backup in case they lose power. It allows them to get to the next station, have control of the train, open the doors, and run the air conditioning. And then we also have 3,000 batteries installed in energy storage as well. So with all of those different systems that we've done applications with, we have produced over 4.5 million cells and deployed those in the US. So it's pretty interesting because sometimes at some conferences when we're doing presentations, they'll introduce us as a new technology. We've been commercializing this technology since 2000 with an impeccable safety record, and customers and the industry is just beginning to see all of that. So it's been a very exciting time for us to grow. And you know, when you go into a customer and they start to realize some of the benefits of this chemistry over others, and the light bulb goes off, it makes our job extremely fun. Okay, next slide. Okay, with that, I'm going to hand this over to Renato so that Renato can go through the heart and soul of the chemistry and the battery applications, and also discuss the role of the batteries in decarbonization.
Okay, thank you, Cara. Thank you, everybody, for your attention. My name is Renato Manzoni. I'm a product application manager. I was looking first at the beginning mostly on mobility application, but in the last year the market changed, and I'm also looking on other applications, backup and stationary application as well. I'm working in the company since year 2000, so I've seen many projects, and I've seen the development of this technology in the last 20 years, let's say. Okay, first of all, what is the basics of our battery and in general of all the batteries are the cell. We have a cell that use some very simple material. Let's say we are using the sodium chloride, so the salt, the common salt, and the nickel as basic materials for our reaction. And then when the battery is charged, the salt and the nickel will react together, and that will create the nickel chloride and the sodium ions that will be generated only when we charge the battery. The cell is taking the use of a solid separator, which is a ceramic, a beta alumina ceramic, that has some characteristics that are unique. So the beta alumina ceramic is able to allow to transfer only sodium ions to pass through the ceramic. This gives to the cell a unique characteristic that the cell has not a self-discharge, an intrinsic self-discharge that is on the other way common from all the other chemistry that we have that are available. The other characteristic of our cell that it is working at high temperature. In order to get the reaction active, we need that the salt and the sodium should be in the melted condition, so should be liquid. And then in order to have a reasonable internal resistance, the temperature should go in the range of 250 C upward. So our battery is working inside at high temperature. This is also not unique because there are some similar technology. You can think to the sodium sulfur or something else, but it is not common, and it can have disadvantage because high temperature means that you need to heat up and so on, but this will go to be an advantage, especially in certain conditions that I will try to explain later on. If we go a little bit more in detail on the cell, we have here a picture of the cell. Our cell is a cylindric cell with the case which is a metallic case. The metallic case is also the anode, is the negative pole of the battery. Then we have inside what is a ceramic separator that is in both sides a separator and an electrolyte, and is separating the positive, the cathode, the positive compartment from the negative compartment. The part outside of the negative of the ceramic, when the cell is say virgin and has never been charged, is empty, and then when we make the formation of the cell, we start to generate sodium inside the cell. On the other part, on the cathodic section, we have the active materials, which are, as I mentioned, salt and nickel. In reality, we have a mix of metals, so we have also some iron for the reaction, but the main compartment, the main components are salt and nickel. And this is the reaction, charge and discharge, and there are no side discharge. What is interesting is that in order, as I mentioned, the ceramic will allow only the transfer of sodium ions, so that pass from in one direction or in the other direction. And this means that this may happen only if there is a voltage applied outside the cell and there is a current running outside the cell. So we have a transfer of sodium ion, and then the electron that is coming with the current will go from ion to liquid sodium. When we charge the cell, the tank, the external part will work as a tank, will be filled up, and so the level of the sodium will increase and will go up. When we discharge, we will reduce the level of the sodium. There is another detail that in order to keep the internal resistance constant during the full charge and discharge, independent from the state of charge, we need that all the ceramic, or most part of the ceramic surface, will need to be wet with liquid sodium. This can happen because we install these springs, metallic springs, that has two purposes. One is to give a mechanical stability inside the cell, and the second is to create a capillary gap. In such a way, the sodium will goes up in the capillary gap and will wet all the ceramic and will give all the surface of the cell available for the discharge mode. I have a short video to show you what happened. Batteries in the past were known as also as zebra batteries. So you see in the charge cycle, and we have the formation of the sodium out of the ceramic. In the discharge cycle, we have the opposite direction. And that's all what happened in this, in our cell. So I mentioned that our batteries and our cell works at high temperature. So of course, 250 C, let's say 250 C centigrade. This means that we need to build around the cells a thermal insulation. So the battery are integrated in such a way that there is the cell pack where the cells are connected in series, typically in series, and then in parallel, with chain in parallel to get the right capacity and the right voltage of the cell. Then cell have a mechanical box, so need to be insulated, and as insulation we are use mica layers, which is a very good insulation also at high temperatures. And inside the box, inside the cell pack is built inside what we call the inner container, the inner box. In order to get the thermal insulation, we need an insulation system which is done with silica-based material that need to be with a certain thickness in order to get a good insulation. You have to think with a mass of cell that are at 250 C, and the thermal insulation should give a battery box that has a very low thermal dissipation, and so have a very rise of the temperature above the ambient of the 1 or 2 degrees. So we need to have a very, very good thermal insulation. So this is done by having an appropriate level of the material, of the insulation material, and in some application using the vacuum technique to use to reduce the size of the insulation and then to reduce the size of the battery. Then out of the battery, out of each battery, we have an MBS, a BMS, a battery management system that take care of the thermal management of the battery. So we need to heat up the battery, so there will be some heater that need to be activated using the power available from the DC link or from the source that is available in specific condition. And the BMS will also take care about the correct usage of the cell, so we'll check for the proper voltage, proper current condition, and will be able to isolate the battery and to protect the battery in case the system will try to make some overload and put the battery in a situation which is not safe or good for the cell. Okay, what we are doing in FZSoNick, we are doing almost all the process that are necessary to get the product. So one process that is under our control is the ceramic. So we build the tube, the ceramic tube, which is beta lumina. Beta lumina is a special kind of ceramic that, as mentioned, allow the transfer of the sodium ion. This is built by, say, starting from the raw material, creating the raw material with the right granulation, then the material is pressed, then the ceramic, the component is sintered to get the ceramic strong enough to be to stay inside the cell, to make its job inside the cell, and to stay alive. What we have also, of course, the cell needs to be sealed, so we have on the top a special alpha lumina collar that allow to seal the cell to avoid that the material that are inside the cathode can go outside, and where it is possible to connect the negative pole and the positive pole. Then another part of the production is to produce the powder, what we call the powder, which is a mix of mostly nickel, iron, and some other minor components to stabilize the component, that is the active mass that will be filled inside the cell in the production. So this as a process to get the right sizing, because when the say the material is inserted inside the cell, it should have the right granulation in order to allow the presence of the electrolyte that work like a sponge, where the electrolyte can move and can allow the moving of the ion inside the cell. The cell is assembled. So the cell, you have seen here, the cell is done by a metallic case, then a ceramic, the shims, the cover that is laser soldered, and the positive compartment that need to be filled with the current collector, which is this part, and then with all the material. So the cell is, let's say, assembled in a cell production line. Each cell is sealed, is tested for the sealing with helium leak test, is tested with X-ray in order to see that the level of the materials is and the position of the current collector are in the right position. So there is an 100% test of the virgin cell during the production before to go to the integration on the battery. And then finally, in stadio or in V1, there is the assembly of the cell pack. So the cells are packed together. They are connected by an intercell connector, which is soldered on the top of the cell in order to create a chain. And once there is the definition of the string is complete, there will be the first charge with the activation and the formation of the cell of the battery. This can be done directly by the BMS, that at least in one type of battery, in some types of battery, can be done directly by the final BMS in order to facilitate and make easier the production. Then all the batteries are tested for the performance. So we have a performance in terms of how much capacity is taken from the string, and in mostly for the automotive battery, in the measurement of internal resistance during what we call the acceptance test, and then after this they are completed and can be delivered to the customer. What is one of our characteristics? That we have very, let's say, simple and simple materials, which is very common. We are not materials that are difficult and that are difficult to be found or are going to. I mean, probably you know all the history about the cobalt and the availability of the cobalt and availability of the lithium that is under discussion for the lithium-ion batteries that are the availability is not well spread in the world, and then there could be issue and there could be more issue in the future. Our basic material are sodium, salt, which is very common, nickel, which is common as well, and then we use a ceramic where the basic material are fine. We have no toxic materials, and what is important, and we will see in the next slide, that all our battery is completely recyclable. I mentioned our basic material are nickel, iron, common salt, and ceramic. When we have a battery that is at the end of the life, we can use the battery as is without the need of any workaround of the battery as let's say raw material for the production of steel. So we have our second life. The second life of our battery is to be a production of steel. So a battery at the end of life has still a value, and the recycling cost is already included in the selling price. So what is under discussion for other technology? What we'll do when the battery will expire, when we are at the end of life and so on, and all these questions that are coming, that are arising, and then are giving also idea of second use of the battery. For us, are not, let's say, are not an issue, because we have already established a process for the full recycling of our battery. So once a battery will be scrapped, will be end of life, we can have from the battery steel and our component used for asphalt. Okay, we are on the market since I would say 20 years at least. We are in different markets, so to stay there, we have done different kind of tests, and these are example of some tests that has been performed, test and certification. Of course, we have done short circuit test, over discharge, shock and vibe test for in different conditions and so on. But what I want to mention is that we have passed the UL 9540A test, and we believe to be the, at least at the moment, the unique battery, the unique technology that get a UL 9540A certification for both cell and module level. This is the evaluation for the thermal runaway far propagation. So our batteries resulted very, very safe. And then, okay, if we have a fault, an important fault of the battery, we could have a little bit of smoke coming out of the battery, but not more. No explosion, no risk explosion, no risk of fire. And so you see gas component after flaming, no flaming occurred, and so on. So I believe this is one of the safer battery that you can find on the market. If we try to make a comparison between the technology, you can see that
our battery, the sodium nickel, as say, is well scored for in terms of energy density, in terms of safety, and in terms of life. We are an energy battery, so the power density is lower than, for example, our batteries like some lithium-ion chemistry or as well. I mean, lead acid battery are a little bit. No, not this one. These are a little bit better in terms of power density. This comparison is done especially taking in consideration the say application for backup application. As well, this comparison. So one of our highlight that we think is very important is the expected life. We are speaking about calendar life. So our cell is that do not have any side reaction if kept in standby. Let's say and this is when happen in the typical application for backup. The battery stay there, is ready to let's say, give energy if the main power is going away, and then stay most of the time in standby. In this situation, our BMS will stop the charging process. We do not need to have, we do not have a self-discharge intrinsic in the cell, so we do not need to have a regular fill up of the battery. So the battery stays there, the reaction is stopped, and then there is no aging in this life. So we will expect a life of, and we have proven by our test a life of which is very, very long, that can last 20 years. Another important characteristic of our battery is that we are at high temperature. Having the chemistry that is working at high temperature means that practically we don't care about the ambient temperature. This is also very unknown. I believe that you heard about the what happened for example, lead acid battery. Every 10 degrees more in the ambient means that the life is halved. This is absolutely not true from us. We are working at 250 C. If the ambient is 40 or 60, doesn't change nothing. Change a little bit the thermal dissipation of the battery, but nothing from the chemistry. Well, of course, having a battery that, let's say, is working high temperature, need thermal management and so on, we need to have a BMS for each module, which is add additional safety and additional, let's say, security to all the system in order to be sure that there will be not the cell will be not overcharged or over discharged. So the BMS will take care about the well management of the system. Okay, shelf life very long. Initial cost, okay, yes, of course, our cost is high, but we have also a very high energy density. So our energy density is in the range of, at battery level, which is not common, is 130 watt-hour kilogram, something like this. Also for the environment, we think that our technology has some highlights. So depending of the construction, but typically is coming from the BMS, we can allow direct outdoor installation. We do not need we do not need room ventilation, we do not need air conditioning for what we say. So the usage of our batteries will be relatively simple, and well, we will have let's say a safe way to store the energy. We can provide a safe way to store the energy. When you mean we have a BMS, I mentioned it. The BMS is able to detect if there is anything not correct inside the battery. So we are able to detect, for example, a failure of one cell. And typically, a failure of one cell is not, let's say, something that could affect the operation of the battery, because a failure mode of our cell in a short circuit. So as the cell are connected in strings, losing a cell means that the string is still available. It has a little bit lower voltage. We lose one cell as voltage, but the string is completely available. So we are able to measure this to eventually advise the user that could be necessary to make some maintenance. And that's it. The battery is will work also in case of some minor fault inside the battery. What we think, of course, every product need to be improved to stay on the market and so on. So we are working in different directions, and so we are looking for a new ceramic powder. So we are going very close to introduce a new ceramic powder that will likely reduce the internal resistance or allow to go a little bit lower in temperature. And we are, in order to improve the reliability, we are going to improve the design of the cell. And we are designing new BMS with advanced feature in order to keep the battery, to follow up the request of the customer. And we are growing up the family of the product that we are presenting on the market. And then on the other way, we are working to improve the process and the production, making investment to improve the filling process and to add some assembly lines for the cell in order to be ready to follow up the market that we see is growing up fast. Okay. Starting from this cell, so our cell, we have different families of products. The main characteristics of the batteries are in terms of performance, are the immunity to the temperature, to the ambient temperature. So we can work very easily from very low temperature to very high temperature, and the limitation is coming typically not from the chemistry itself, but from the electronics, so can be managed. The cycling capability is that we have seen in the application, and reapplication is high. So of course this depends on the application, but in stationary application where the cycling is well controlled, we have seen up to 4,500, 5,000 cycles. We have very low degradation as calendar life, and we have a good energy density. So our shelf life with the battery in standby, is more than 20 years. This is really not common, especially if we think that this can happen in ambient with very high temperatures. Okay. Another highlight for our technology is the safety. So our cell or our chemistry is not so reactive as other chemistries. So what does it mean? That also in the worst case, we do not have the generation of flammable materials, the exit of flammable materials, and we in the normal use we have no any kind of emission of gases. All the cells are sealed, and okay, in case something strong happen to a battery, like a crash in a vehicle application, if the ceramic break, and the ceramic is the more fragile part of the cell, if the ceramic breaks, the result of the reaction after the ceramic breaks are salt and aluminium. So are all material that are once the temperature go down, are solid materials. So there is no flammable materials and no very dangerous material. Then we have, we call our battery as zero impact, okay, because our battery is 100% recyclable. So as I mentioned in the previous slide, the content of nickel is a value also when the battery will be scrapped. So this battery, our batteries will be suitable for different markets. We are very good in telecom market, where especially if in the ambient is very harsh. We have oil and gas, offshore, safety very important in this kind of application. I believe railways application, energy storage, and fuel electric vehicles. Okay. To have a short look on the our range of batteries. This is a battery that is 110 volt, is a backup battery for railway application or for signaling for railway, used for signaling for railway. Is about a 9 kilowatt-hour battery, 80 ampere hour, and 110 volt DC, with a controller that can allow the communication via CAN to give all the information of the batteries. Tested for railway application and I will use it on train. Another family of battery that are for backup application, ranging from 48 volt, 200 ampere hour to 250 volt, for 40 ampere hour. All the size is always in the range of 9-10 kilowatt hour for this battery. Application, I can think to, let's say, in general backup, we are customers that are using this battery for UPS, our battery in the switching station for the grid, and so on. This is a 48 volt battery, the 48TL200, which is the mass produced from us, used in telecom and in data center, for backup in data center. It's a typically battery used for application, and we have also some use of this kind of battery in some together with solar panels for remote use in remote countries. For the big energy storage, we go high in voltage. So we have a battery which is running 620 volt DC. This is 620 volt is the open circuit voltage, 38 ampere hour. And battery that are used in, let's say, relative big energy storage. If you start from a cabinet, or that go down to container application. One container of this type can store, let's say, 1.5 gigawatt hour. No, 1.5 megawatt hour. So 1.5 megawatt hour of storage in one container, and we have installed some of containers like this. Finally, we have a range of battery that are used for mobility applications. This kind of battery, of this family of battery, in order to keep the dimensions compact, will use the vacuum technology in order to reduce the size of the isolation. So I showed you before that we have an inner box and outer box. In this case, these two boxes are sealed, and the battery work, and the full case work as a thermo bottle. So we take out the air, we use the vacuum to reduce the thermal dissipation between the inner and the outer box. And in a special application, we have also developed a battery system that see in parallel the use of our battery and a supercap, our batteries and the supercap. This is the supercap is used to say provide the peak power, very fast peak power that can be necessary for the driving. I can get the very fast regenerative braking, and the battery will provide at the end the range to the vehicle, the energy to give the range to the vehicle. So power typically, at least at the beginning, from the supercap, and then the range from the battery that can be connected in parallel. What is, I would say, characteristic from us is that we can use the supercap and the battery together in direct parallel, because the characteristic of the internal resistance of the battery will match very well with the characteristic of the supercap. So the supercap will be able to provide the power because the voltage is moving, and the battery will provide the main energy to the system. So this without a DC-DC converter. Okay, how we see our batteries, or in general batteries, helping for the decarbonization of the transport. First of all, these data are from the International Energy Agency. So the 42% of the emission of CO2 is coming from the electricity and heat production. The 22% of the emission are coming from the transport. And then the transport is shared between different actors. You see car, you see trucks, and you see, let's say, airplane and ship and other railway. So, okay, where it is possible to act? Okay, it is possible to act for the transportation. It is possible to act to the configuration of the vehicles. So the configuration of the vehicles, okay, depending on the type of the vehicles, we have different emission in considering in CO2 equivalent per kilometer. So you see, we can have the standard cars with internal combustion engines that today is the green level, the black level are in the range of more than 200, and then that is going down depending on the level of electrification of the system. If we have hybrid, plug-in hybrid are less, and so on. And this is the trend that it is expected in, say, 10 years from now. So, but cars are improving, and the level of electrification is improving as well, the emission of CO2, but maybe not enough. Then we have the electrical vehicles, and there is a lot of discussion about electrical vehicles. Electrical vehicles has no direct emission, no local emission, but we cannot say that they are completely clean if they do not take the energy, the electrical energy, from renewable sources. So they can move, if the energy is taken, the electrical energy is generated by coal, for example, we can just move the size of the pollution. The vehicle can be and will be more efficient, so will help, but the advantage of a pure electrical vehicle will be not so high as will be if there is the generation that is coming from the renewable. So batteries can do two things. One will be the main component for the electrified vehicle. So in all the vehicles that are at a certain level of electrification, starting from the mild hybrid to the full hybrid and so on, we have a battery inside the system that is able, a certain level, to help and to reduce the consumption. If we go up with the hybridization, it will be able to recover energy from the braking, and then it could be able to let the vehicle run in pure electric mode and so on. And this will be one use of the battery to reduce for the decarbonization. But I mentioned electrified vehicles. There are not only cars. What I mean is that there are not only cars. We have also, for example, buses, and we have to remember that one bus, the usage of one bus can be equivalent to the usage of more than 30 cars. So you can understand what this can mean in terms of occupancy of the way, in terms of traffic and so on. So bus can do electric bus, and electric bus can do a big job for the decarbonization and the reduction of the emission of CO2. Another important thing that the battery can do is the increase of the penetration of the renewables. If you take, for example, the sun, we have a graphic of the sun that the production of the sun is something like this during a sunny day. So there is a production that is start when we start to have insolation, that goes up and then go down during the night. And then this may be not related with the need of energy. So there will be, in order to be able to use the renewable, the energy generated by the renewable, we need to have a system, an energy storage system that can allow the shift, the so-called load shifting. So make available the energy that when it is necessary, and be able to offset the energy and to take the energy from the generators when the energy is available from the generator. So it's the load shift. So batteries can do a big job and are doing a big job in this direction. So our batteries are in the market since the 90s. So then Nestlé, I'm working in Nestlé since 2000, starting in 2000, we were, at the beginning, we were dedicated typically to EVs and hybrids. Now today, and this is when, say, the Thiam group came on, we broadened our application in different fields. And okay, our contribute, what could be? Could be to have batteries used in, let's say, professional application, utility vehicles, electrical bus, hybrid bus, delivery vans. So our battery is not, say, anymore an option for the for car application. This is because I would say two different things. One is the energy density. So I have to say that the energy density of lithium-ion is higher than our, and then the demand of power in the car is growing up very fast. The demand of power for electrical car is growing up. On the other way, our battery are well fitted in a system where there will be a certain amount of energy to make a full service. Full service, I mean, stay in service for 10, 15 hours every day and make a professional use, and are very, very well suited in harsh environment. So I see the application for our batteries in transport in these two fields, professional application on big vehicles and harsh environment or harsh environment. As well, the same, our batteries has been used together with PV plant or wind generation in order to match the production of electricity with the use of the electricity. Some examples, we have bus application in very, very different ambient with similar kind of batteries. So we have the same cell, the same principle. So we have bus that from very cold, we had a fleet of buses running in Canada, buses running in the desert in Abu Dhabi. And we have different professional application, I would say. One of our customers is Motive Power in USA and produce let's say a set of vehicles that have different use. We have school bus. We have, for example, a fleet of shuttle buses as this one that are used in Mountain View from Google. So it has been given from Google to the community in order to have a free local transport. And they are all basic on a chassis that is a Ford chassis modified by this integrator. This is the first EQVM certified producer. Our application so we have school bus, shuttle bus, or van for the good delivery, or sorry, something went wrong with the presentation. I'm sorry. Okay, I am back, hopefully. Okay. Our application, bus application, fleet of buses with our batteries running in Europe. The manufacturer is Irizar, based in Spain. Or what I mentioned before, it is another delivery van or that can be also configured as minibus with Iveco, that is a pure electric, where you use this combination of battery with a supercap. Then other applications for our batteries are this microgrid application, where we have, for example, in Lago e Sile, a village that is completely powered by a microgrid with a PV plant and an energy storage of 560 kilowatt hour. Okay, and then some other reference for our project. These are some let's say names of our customer for energy backup. You can see Ericsson, you can see TNT, Telcel, Verizon. For sustainable mobility, I mentioned Iveco. Then I mentioned MindMaster and SoNick for other application that I will show you shortly. Bombardier for the train application, and then some major utility for the energy storage, like Terna and Enel in Italy, Schneider Electric in France or everywhere in the world, Itaipu Binational in Brazil, and A2A. Okay, not so many comments on this. This is another something that I want to comment again. So mining is let's say a good application for electrical vehicles or electrified vehicles. Why? Because one of the major costs that is in the management of a mine is the cost of the ventilation. People are working very far away, are working in very harsh conditions, and the usage of diesel-driven machine will make the ambient very polluted, and then the need of the ventilation very hard. The usage of electrical driven machine will help a lot to improve the quality of the life of the miners. So because of this high cost of the ventilation in the mining application, so the additional cost that is can be related or is related to a pure electric vehicle against a standard diesel vehicle or diesel machine, let's say. I mean, the additional cost is compensated very fast, so by the usage of electric, because of the reduction of the need of the ventilation, and this will help to have a fast or relative fast introduction and without incentives in the mines. So we have our customer that are producing a machine like this. This is a drill. Drill is a big machine that is used to make the holes in a mine, in the material of the mine. They also were to put the blasting material, so the machine is standing to make the holes, and then is moving, and when it's moving as pure electric machine. You can think it is a machine of 30 meters long and 25-30 ton weight of 20 ton. So big machine moved around in the mine by battery, and in the mine one of the things they are looking is the temperature ambient that can be very high, and that's the safety, because in case of something happen, there is a fault, the system need to be as safe as possible in order to save life. Other machine will be this dozer, which is a low profile machine done with for special mine where the vein is very low in height. And some other example with some other producer machine. This is another machine, but a battery electric load and hauler that with the battery installed in this box that are able to provide enough energy to make a full day of operation of the system without pollution inside the mine. For other applications that we have for transportation are on train. We have batteries that are used by Bombardier in some metro lines in the world. You see Brazil, Saudi Arabia, Malaysia, China, Thailand. And our batteries are batteries suspended below, so outside, below the train, that are used for the backup of the service when the train is stopped. Or we have also our batteries used for signaling in railway application. You see South Africa, Switzerland, and USA. These are big data center, battery for the backup of big data center with very important brand names, T-Mobile, TNT, and you see US, Russia, Philippines, everywhere in the world. Another interesting project, this is, let's say, is the so-called Vilaya emergency system developed by Schneider that use the 48-volt DC battery, and in a container they keep the battery system, and they keep they can transport the solar panels to create a microgrid for emergency situation or for remote villages typically designed for let's say country under development, for typically for Africa. We have this application in Africa. Also here, ambient, very harsh, very high temperatures, and our battery are fit very well. Already mentioned Petronas, oil and gas, harsh environment as well. We can stay. Our batteries do not need to have a dedicated chamber for batteries and so on, so we'll give, let's say, a good gain in terms of volume and space available in the installation. Okay, this graph shows what happened in terms of temperature in a system that was outside in test of 1 year. You see how many times the system went to 60 degrees, and then we have no issue at all with the battery system. And microgrid, big microgrid, for example, in some remote location, in some island, where we can support the local network and optimize the use of the diesel generator in order to reduce the consumption. Or other application typically connected to the grid for the maximization of the transport of the power grid from the from the, let's say, mainland in Italy and the island Sardinia. Okay, to conclude, I would say that in order to have a reduction of the global emission, there will be necessary to have a coordinated action from different actors. Then another statement is the batteries are an enabling technology for the global emission, and then the demand is very diversified. There will be not a unique solution that cover all the need of energy storage, and we can do our part in heavy duty and professional vehicle and in service for the electrical grid. Thank you very much for your attention.
Thank you so much for this excellent presentation to both of you, Cara and Renato. We certainly enjoyed the introduction to the company and learning about the first principles for the salt battery. And I learned a lot myself with regards to this new type of battery, which we haven't seen around a lot. So what I'd like us to do now is to look at the question and answer session. Although we're ahead of schedule, but I think because we have many questions, I suggest we take as many as we can during this session. And then if we run out of time, we will then maybe reply to the questions in writing later, so that all questions are answered. Right. I'll look at the questions that we have on our board and just start from the top, going down. I think this first question started when Peter was presenting, saying, what about electric HGVs? And this is someone working, I think, for a client, and he's asking about this question.
Yeah, well, it's a lot of interest. And as was just shown, for example, in the bus applications, there's been a lot of battery being used nowadays. Because, of course, they're on a fairly confined route with a predictable load pattern and so on. Trucks are a bit more problematic. It depends a bit about what you mean by trucks. The light commercial vehicle sector, that's going to be a booming application for these kind of technologies, because of course we've got a couple of things going on. The desire for clean air, the transition from physical shopping into sort of online shopping and having products delivered, both of which have been sort of accelerated by the pandemic. And then of course the technologies kind of fit that pattern again, because you've got very predictable routes, you've got predictable loads, back-to-base charging as possible, and so on and so on. The trucks, or heavy-duty trucks, they are definitely more of a challenge. There's been quite a few trials going on with, for example, the use of overhead electric wires, as you see in some train systems. And of course, there's a couple of the US companies have been busy promoting trucks, including Tesla. But at the moment, I think for most operators, most of the time, the economics of that simply don't stack up. And as you're probably aware, mainstream commercial vehicles, that's a very, very cost-sensitive industry. The margins are tiny. The pressure from their customer base is huge. And so they don't have a lot of flexibility when it comes down to offering alternative solutions. Yes, they're coming. They will come more. But there are those kind of constraints, which I think at the moment at least are holding the whole kind of sector back a fair bit.
Okay, thank you for that. Anything from you, Cara or Renato, with regards to HGVs and electric HGVs?
No, from my side at the moment, no.
Okay. All right, so we move to the next question. I think this is a financial one. Peter, what is your advice on purchasing an e-car, considering the financial side?
Well, two pieces of advice. First, I would never advise anybody to buy a new car. the depreciation over the first 3 years is horrendous, and that applies also to an electric car. Secondly, perhaps you should not buy it with a purely financial viewpoint. I mean, I bought my Nissan Leaf used, knowing that, you know, at £12,000, after perhaps 4 or 5 years, that will be it. But I did it because I valued the other things more, the demonstration effect, the clean air, the quietness, the flexibility, and so on. So I think a very narrow financial calculation is perhaps the wrong attitude in that respect. I think overall, nonetheless, over its kind of life cycle, if you look at the initial cost, the depreciation, slightly higher insurance and lower fuel cost, the differences aren't that great with a traditional petrol or diesel car at the moment. The real hit is that there's not a proper second-hand market. There's not a proper used market for these cars. And there's not enough servicing out there. There's not enough kind of wider support. So it is at the moment still slightly riskier financially and in general to take up on an electric car. Those things will change. The more people go down this route, it will change. I was reading yesterday about the huge volume of investments. $300 billion was a recent estimate being invested in new electric vehicle products worldwide. That's a huge amount of money. So there's going to be a lot of choice and a lot of interest. And by that time, maybe also new ownership patterns, new ways of buying and using cars, maybe pay per kilometer. Maybe you won't have to actually own a car anymore in that sense, and maybe you know, you'll be able to pay for it on a per-use basis. So I think with these new financial arrangements, the pain of handing over a large wad of money perhaps will go away, and we'll look at something a much more flexible, more attuned to current circumstances, more attuned to what the electric vehicles can offer. And so I'm kind of hopeful that a combination of the technology improving and the kind of ways of owning and financing vehicles changing, we'll see more and more growth in that area.
Okay. So the next question from Samantha Jones is directed to FZSoNick. Does FZSoNick have a battery service / rental model in place with any of their customers?
So, I believe we have to coordinate the reply between us. Say, maybe, Cara, can you say something about what we are doing in the States for the telecom market?
Yeah, so currently we are evaluating how we approach the market with the batteries, but we don't have a rental program right now where we ask customers to pay for the battery over a period of time. We've looked at potentially reducing the CapEx and providing a lower cost for the battery, and then adding on a cost per battery per year for a warranty cost. The batteries can be repaired, so our dynamic is a bit different than other batteries. We have the advantage there that if there is some sort of failure, that we can replace a cell or a BMS in order to get the battery back into service. But nothing formal from a rental standpoint yet, but we are evaluating new services and things to bring to the market.
Okay. Can I just ask a question on this, Cara? I mean, is it the case that it's the you don't want to hold the financial capital cost that makes it less attractive to you? Because obviously, you know, if you tie up assets in that way, it's on your balance sheet. Is that the kind of thing that's driving that decision, or is there something else going on?
Part of it is the market that we really deploy the batteries in to start. I mean, in an energy storage system, they are looking at more creative ways to manage the cost of an asset over time. So you'll see in large-scale energy storage systems, some companies will release the kind of a rental program where you're paying for that asset over time, and that company is owning it from a financial standpoint. In our U.S. market, we've really been focused on energy backup, so telecom, utilities, oil and gas, and their model has still been to purchase the batteries outright with CapEx, and then they look at the reduction in OpEx in the back end as part of the total cost of ownership. And yes, from a financial standpoint, kind of taking that all in-house as a smaller company would be something that would be difficult in the beginning.
Okay, thank you. The next question is, again, battery related. With all the benefits of this battery, which meant, I think, your battery, why don't we generally hear more about it? Why is it only rare earth-based batteries, which are mainly in the press, etc.?
That is a great question, and one that, you know, when we were presenting to Chevron, for example, they're like, why have we never heard of this? And my response jokingly was, we're the best kept secret, but that is frustrating. So one of our main competitors, because we are an energy dense battery, is lithium ion. A lithium ion battery supplier, anybody can go and buy the cells from Hitachi or LG and make the battery. So there you have hundreds of people out there buying these lithium cells and making a battery and putting a battery management system on it. So you're also having a really wide range of quality batteries out there. Some are safer than others, and some are not so safe because they're being made by small shops. So when we would go to industry conferences and have exhibits there, you would have our booth with the sodium-nickel-chloride battery, and then you'd have hundreds of booths with lithium-ion suppliers. In my mind, I thought, well, there's all of these suppliers and there's not as much demand. So the supply-demand curve says that the price of the batteries is going to go down. They're going to be very low margins, and a lot of these suppliers are going to fall out of the market over time, leaving a few big quality lithium-ion battery suppliers in the market. But what I've recently learned with some competitive intelligence is that a lot of the suppliers are Chinese battery manufacturers. And even though they're not really profitable, they're still being subsidized by the Chinese government. So there really hasn't been this natural attrition of the suppliers falling out of the market. But, you know, where we're gaining traction is, you know, we're also a very engineering oriented firm, so we're not as great at marketing. But where we are finding traction is that when we get a customer like Exxon, who we speak to about the technology, and we find a lead user that's willing to change and move from something like lead acid to something that's more energy dense but safe, they really take the technology and embrace it, and they'll do presentations on it at conferences, and that's where we're beginning to get more marketing into the industry. So you know, our growth has been slower because we are the only manufacturer of the technology. However, GE was making a battery called the Durathon battery before we purchased 100% of Mestia. They were licensing the cells from Mestia. So they were getting the cells from Mestia and they were building a battery. They were focused on the energy storage market. We would go head to head with them in telecom, and we designed our battery with T-Mobile. And because we designed it with a telecom customer, it was really designed very well for the market. So every time we went head to head with GE in that space, we won the business as a small company versus GE. They did validate the technology in the market, but because they didn't have a lot of diversity across different verticals, they ended up closing their manufacturing plant in the US and getting out of the business. So then we were at shows and they'd say, oh, that's that sodium-nickel-chloride battery that GE made but isn't around anymore. And we would say, well, no, we're the original manufacturer of the technology and we're still here. So we are growing, but more slowly. But I think as more and more big companies understand the technology, that marketing piece will come.
Okay, thank you. So the next question is from Omer Rana. It says, excellent presentation, really learned a great deal about battery technologies. What is the weight of this battery for a typical vehicle?
Okay, thank you for your comment. Okay, I can say that so our batteries are modular. So we are module for the mobility application, which are in the range of 21 to 27 kilowatt hour. and then these modules can be connected in parallel very easily. Okay, and then I can say that a module of 21 kilowatt hour is about 180 kilograms, 190 kilograms, 185 kilograms, if I remember correctly.
Okay, I think there is another question coming later on weight anyway.
This is the relative to the fast charging, I believe, no?
Now the next question is, yes, are they suitable for fast charging?
Yeah, we call, okay, what is fast charging? If you think to charge a battery in 15 minutes, no. We say that we have a quick charging and then it depends on the state of our charge. We can allow to have partial charging, in the sense that we do not need to fully discharge and then fully charge the battery, but we can have some intermediate charging. And I could give a number that is from 20 to 70% in 1 hour, something like this.
That's excellent.
To give an idea.
Yeah, yeah. Robert Chapman, I think we asked his question at the beginning. That is the HGV electric vehicle type.
To expand a little bit on Renato's comment about the fast charging. Okay. So he went through some of the attributes of the battery, and so we're not a power battery, so we will never compete with a Tesla or a vehicle like a commercial vehicle. Where we look to put the battery in mobility applications is things that have a set route, like commercial vehicles or mining equipment, and things of that nature, where there's a set route of time where they have a certain number of miles, and we can plan for that charging piece.
Thanks. So the next one, I think, again, it's for you, Cara. Will people in North America be convinced to move to smaller cars? Or you think the electric SUV and trucks will still dominate?
No, I can answer this from a personal perspective. You know, I really think it depends on the area of the U.S. that you live in. Certain states are going to, and if you're in a city, the smaller vehicles are going to be more beneficial just for space and being able to park. But if you're in some of the southern states, the trucks are the holy grail here, so nobody's going to give up their trucks or their SUVs. We make big runs to Costco and load up that the trunk with lots of, or the bonnet. Is that the right word? I think the bonnet's the hood part. What do you call the trunk?
At the front. The boot. We can call it the boot.
We fill up our boot with lots and lots of things in there. So, you know, we're still kind of in the large vehicle environment. And also part of that is because gas prices are really low too. I mean, I think if gas prices are low, that drives people thinking about that cost of ownership for having a small or a large vehicle.
Anything to add, Peter, on this?
I mean, I think it's a very interesting problem in a way. Yeah, I say problem. I remember one time going to visit Chrysler in their head offices in Detroit, and I had a typical American hire car, driving along and go to their car park. It's very, very busy. But I thought, oh, there's a space. I go zooming in to go to this space, but tucked into the corner of what is one parking space for a typical American car, tucked into the corner was a Mercedes Smart. This tiny little thing, and it looked so small in that vast space that was available to parking. And this is the thing: is the American infrastructure is built around the capability to look after those things. If you look at the big shopping centres, out of town shopping centres, they have huge parking spaces, and it's all set up. Many other places in the world are not like that, you know, and for that reason alone, the American park, you know, the stock of cars in America has been a real outlier compared to most other locations, particularly you know, Europe and Asia. And so I think in a sense, this shows you that the idea of a kind of homogeneous world market for cars doesn't exist, that there is this great diversity. And the kind of choices that Americans are making about their cars, you know, reflects a whole bunch of things, partly cultural, as Cara says, partly economic. I think they will also change with time, though, you see. that there will be perhaps an appreciation that there are a lot of disbenefits to having these great big vehicles, and that they are very, very inefficient. And so, you know, here in Europe or other places that are very, very congested with much smaller spaces and so forth, you're never going to see many of those things. And when you do see a Dodge Ram crawling through the streets of Penarth, it is so clearly out of place. This vast device rolling across our streetscape. It just looks inappropriate. And of course, then you can't park it anywhere, you can't drive it anywhere, and so on. So, yeah, the American case is a bit of an outlier, I think.
Okay, thank you. The next question is from Samantha Jones. The battery problem now looks a bit like the old engine problem used to be. What did we do when the engine needed replacing and it cost more than the car is worth? We replaced the engine as long as it cost less than a replacement car. And we could guarantee the number of extra years of car life if we were buying. So I guess here is the cost that you talked about, Peter, earlier, on replacing a car after 8 years, and what do you do?
Yeah, sure. I didn't appreciate until the presentation the modularity of the battery that Cara and Renato were talking about. You know, to have that flexibility to change elements of the whole pack changes the equation quite dramatically. I believe BMW can change modules within their battery pack. But you look at something like the Tesla approach, it's just one big thing, and that's it. And so, yes, to some extent, the question is correct, that there is this replication of the old problem, which happens, of course, in a sense, across the entire vehicle. You know, if your vehicle is so old and so tired that if you have a puncture, you have to throw the car away, then, you know, that's your trigger point. It's no longer worth your while to invest in a new tire. That problem pervades the entire vehicle. It's just that at the moment, the battery is such an expensive element within the total equation, you know, as a single element, that it outweighs all the others. And as we drive down battery prices, so that kind of risk, in a sense, should reduce, as long as it's still possible to replace the entire pack if need be. When I actually raised this question with the Nissan dealership, they just looked at me rather perplexed. Why would you ask this question? Seemed to be their response. So at the moment, they're not even set up to do this. You know, so I think this is what I mean about the wider infrastructure and the wider support systems and so on becoming into place, that it becomes possible to contemplate even replacing the battery pack in your battery electric car at whatever point in its life cycle that you happen to have it. And then people can make those decisions, or they can cherish their cars, as I suggested, you know, with the old Ford Escorts, and keep them going beyond the kind of narrow economic consideration because they want to, you know. And because they have some sort of emotional engagement with the car or whatever it might be. We're not there yet, and it's going to take quite a long time to get there, I think.
Okay. Anything from you two, Renato or Clara, on this? Or
I have kind of questions in my head, because this whole lithium-ion battery piece at the end of life is always a big question mark for me. When we're able to recycle our battery 100%. There's a significant cost to recycle lithium-ion battery if they do it. So, I mean, Peter, in your opinion and your experience, who bears that cost, and what does the current environment look like for recycling these batteries? Because you're buying a car to be greener. However, the lithium is mined. It's mined, it's not readily available, and you know, how do we keep the greenness of an EV with some technologies that might not be as friendly at their end of life, or if there's an issue where it catches on fire and it has toxicity to it with the smoke and everything else it's releasing into the atmosphere?
Oh yeah, it gets worse and worse. The more you look, the worse it gets. I mean, you're absolutely right, Cara. I mean, firstly, from the supply side, it's not just the lithium; it's the cobalt and the copper that go into these vehicles as well. And as you know, most of the cobalt comes from the Democratic Republic of the Congo, and there are a lot of concerns about the conditions under which many of the miners work and so forth. So, supply side, big problem. And then when it comes to recycling, then yes, again, we have a whole bunch of issues in there around the value of the battery pack and so forth. And the solutions aren't great, not least because once you separate the old battery from the vehicle, then the battery becomes hazardous waste. And that means it needs special transportation. So it needs to be contained in some way and to be made safe, precisely for the kind of fire risks that you identified. There's some great videos on YouTube, if you have the time, of lithium-ion batteries blowing up in storage. There are real concerns about storing these old packs and then moving them around the place and then discharging them in some way that is safe or disassembling them in some way that is safe. That's really been the focus of the Relive research project that I'm involved in at the moment, is to find safe ways to deal with these things. And then you've got a disposal problem because once you've extracted out the cobalt and perhaps the copper and so forth, then you end up with this kind of black mass of lithium, which so far nobody can really use. And you've got to do something with it. The leading contender at the moment in Europe is a company called Umicore, which basically chucks the whole lot into a big pot and heats it up and smelts it, extracts the valuable metals, disposes of the rest. That's not a great solution either. So in the end, you know, what you're getting is slight improvement in carbon emissions, a significant improvement in air quality, and you know, shouldn't throw that one away, at the cost of exactly the points that you've mentioned.
Okay, thanks, Peter. This is a slightly long question from Robert Gibbs. Apart from a very few rich people, the only way normal people can afford to run a car is because of the second-hand car market. Even the second-hand car market is getting more expensive because of market forces. My car is 20 years old with my budget and usable. With only an 8-year battery life, no electric vehicle will ever be cheap enough to buy on the second-hand market. Millions of normal people will not be able to afford to be on the road and get to their work. So the question, aren't EVs all a massively material-intensive stopgap to the hydrogen economy anyway?
Well, yeah, the hydrogen economy, that's a whole other story, I think. I did actually go to, one of the reasons why I went to Iceland, which I mentioned earlier, was to visit them when they proclaimed that they were going to have the world's first hydrogen economy. It hasn't happened yet. Anyway, I think the debate, there is an issue there. I mean, at the moment, electric vehicles can be bought mostly by what I like to think of as conspicuous minimalists. They can show the world how great they are by having the solar panels on the roof and the electric car in the drive and so on at some considerable financial cost. And I remember asking this question myself about 10 years ago at a conference in London, saying, well, you know, what are poorer people going to do about having an electric car? And the answer was, well, they can buy used, and that was it. The questionnaire is exactly correct in the sense that at the moment, there is no trickle down. There is no obvious mechanism by which these electric cars will find their way through to owners who might buy a car that's been through 3 or 4 different owners before it comes to them. I think we will see, therefore, a growth in, despite the COVID situation, a growth in the kind of mixed ownership models, you know, shared ownership models and so forth, which might make that sort of mobility a bit more accessible. And this is why I have some hopes for the more kind of micro mobility sector, because then you've got a much better price performance package. You know, so when you're looking at things like, you know, sort of 2-seat vehicles like the Citroën Me or the Renault Twingo, you know, these are expensive, but much more affordable than a full-scale electric car. So rather than spending sort of £60,000 on a Jaguar I-Pace, you can spend £6,000 on a Citroën Me. And those new prices will filter down to become used prices in the fullness of time. So I wouldn't give up hope yet, but then in the meantime, you've got to wait. And that's also a slight disadvantage. You know, how long do we have to wait for ordinary people, as described, to get into this kind of ownership? I think that's another big problem there. It's potentially quite socially divisive, particularly if you start shutting off parts of cities to non-electric use, and which is happening. You know, it's happening around Europe now. So I think we have to be careful here that we don't end up with basically people who are impoverished by virtue of the fact that they can't go places because they can't get into that kind of mobility.
Okay, thank you. Regarding increased consumption versus economic growth, is car ownership going to become less prevalent and less important in future generations? Will transport as a service become more the norm?
Wow. Of course, I think this picture is very different in America. You see, I think Cara can maybe speak to this as a kind of lay person, but an expert, because you know different cultures are differently kind of orientated towards automobility. And you look at a place like Hong Kong. You know, it's been very affluent for a long time. You know, certainly by Asian standards and even by European standards, but it has a massive population density. You know, I went to a presentation of 15 years ago, and in the presentation, it was provided by the then director of the Hong Kong Electricity Board, right? And very, very interesting lady. And she said that 50% of the population in Hong Kong live above the 15th floor. Now, think about that. 50% of the population above the 15th floor in tower blocks. You don't have to go there to see it, right? Now, at that level of population density, you can't all own cars. It is fundamentally clear. You know, you need a car park equivalently deep underneath every block of flats. And I even had a friend who took his Aston Martin out on sort of 5 o'clock Sunday morning to drive around the streets of Hong Kong, because that was the only time he could do it. But it wasn't so crowded that it was impossible. So it was possible to use his car. So the relationship between your income and your kind of wealth of the country and so forth, and consumption in that sense, particularly around cars, is also very closely tied into issues such as urbanization, population density, the provision of alternatives, the cultural orientation towards, say, using bicycles. Look at the Netherlands, look at Germany, and so on, and the growth of various forms of micromobility. So my kind of gut feel is, yes, we will be able to separate, to some extent, that economic wealth from the kind of heavy material consumption that's embedded in cars, but only by having fewer cars.
I can comment a little bit on this from the US perspective. I don't know if this is I mean, it could be geographic in the sense of cities versus suburbs, but I also think that there's more of a generational trend to sharing versus owning. You know, in the older generations like myself, you know, we're all about owning and having these kinds of assets. And I do think that there's a general trend with the younger generations that are coming up that they don't really want to have as much stuff. So they would prefer to have things that they can share or use as need. So they're more minimalistic than the older generation. So I think that there could be a big trend in car sharing versus owning outright, especially for the expense of owning the cars. And if, you know, these electric vehicles are more expensive, and it limits people being able to buy some of the larger ones that they may need to rent them as needed.
Okay, thank you. So the next question is, what is the cost of recycling batteries? Is there a battery recycling business model? Who are the main players? 3 in 1.
Well, I guess you guys, do you worry about this at all, or is this something you worry about, Cara?
So for us, we actually, the cost of recycling our battery is included in the price of the of the battery. We have an agreement with a company called Inmetco that does the recycling for us. We haven't really, because we have a longer life on the batteries, we haven't really done a lot of recycling, but if we're doing a repair on a battery, replacing a cell, we can send them to Inmetco and provide a certificate of recyclability to our customers. There's really little valuable resale material in the batteries. With like a lead acid battery, typically the consumer that, you know, recycles the battery might get paid for the lead in the battery. For us, we just provide that service free with the price. Now, Peter, you may want to comment a little bit more on what the lithium ion market looks like.
Yeah, fair call. I mean, basically, I think at the moment, firstly, there's not really enough recycling of lithium-ion batteries in general. I mean, not just from cars, but from phones, from laptops, and God knows what else. So there's an awful lot is being simply landfilled, either legally or illegally. Then in terms of the cost, so to speak, then a huge unknown. I mean, at the moment, most of the plants that are able to process car-sized lithium-ion battery packs are prototypes. They're not scaled up fully because, of course, they haven't got the flow of material coming through. And there's a whole range of different alternatives. So just like you've got lots of different battery chemistries and so forth, so you've got lots of different approaches being developed to recycle them at the end of their use. Putting all that to kind of one big bag to one side, I think basically at the moment it's not economic. Therefore, the user somewhere in the system will pay. That a lot depends on what system you're running in terms of recycling in general and car recycling. So, for example, in the Netherlands, there is a fee paid with the initial purchase of the vehicle that goes toward the recycling infrastructure. And that will cover the cost of recycling the car in the fullness of time, and it will be certified and so forth. Other systems are less robust. That's one of our big concerns, is just to make sure the system is robust enough to capture all of these, because you don't want battery electric vehicles being left outside houses like the ones I just showed in my presentation, or parked in fields, left on hillsides, and all the other places that cars get abandoned. That's dangerous, it's bad for the environment. So you need to have efficient capture and collection first, then you have to be sure that you've got a viable processing route. And after that, the economics of it will kind of fall out. But I suspect that there's not enough value of material and so forth in those packs to really make a very strong business case until you've got high volume.
Okay, thank you. The next one is, what is the comparative cost of running an electric car versus diesel or petrol car?
I don't know. I mean, I often get asked this, and I don't care. Which sounds, I'm not that rich, trust me, but I don't care enough about that, because you know, once you've made the decision to own a vehicle, most people think about it differently anyway. For most people, most of the time, they think about the running costs. What does it cost to run a car? It costs how much to stick my fuel in. That's what I think. And so you're not actually really measuring the total cost of ownership. Very few people sit down and do that. And the decision to own and run a car is often not economic. It's about other things. It's about convenience, flexibility, and so on. And under our current system, with our current way of producing and using cars, it still pays us to keep that asset, that declining asset, which loses value by 50% in 3 years, and keep it on your driveway for 95% of the time. So I think the worrying about the detailed cost, in a sense, is a misplaced concern. I would rather question your need for a car. That's the first thing you should do. And then, even if you've got it, question your use of a car, what you use it for and how and why. And then out of that might fall a slightly different view as to how you think about cost. So in the case of my Nissan Leaf, which I previously mentioned, £12,000, I'm only running it for maybe 4,000 miles a year. No, that doesn't make sense economically, you know. I'm doing it for other reasons, perhaps, and for a different kind of logic. And I use my bike most of the time. And I think we'll see more of this kind of thing in the future, that really the total cost of ownership calculation should become more prominent in how we think about car ownership and cost. But then there has to be a realistic calculus. You know, I knew on my BMW 3 Series, it cost £1,500 a year to keep it on the road. Insurance, tax, and the rest for getting things fixed. And then the other part of the money and any other kind of stuff like fuel is additional. If you buy a used car, then that's your calculus, you know. How you go about thinking about your costs, that's the crucial thing. And I think the same with commercial applications for the battery that Cara and Roberto put out. You know, if you think about the way that works, it's most effective in specific settings and specific situations. And so it's thinking about your uses and how you use things and why you use them. That's where you should really start there, and then you think about your costs. You know, there's no point if you're a single person, there's no point you buying a Jaguar I-Pace, to be frank. You know, so think about the kind of usage you need, and then think about what kind of vehicle you want, and then you think about costs.
Okay, thank you. That's excellent. The next question is from Barry Hughes, and it's directed at Renato. What type of strategy you have for research projects in terms of in-kind contribution, time, and much funding?
Well, I'm not sure to understand exactly the meaning of this question, but anyway.
I'll explain because I understand the terms. In the UK, if you want to apply for a research project, you have usually a partner company. If it's the type of projects that you're doing, the company can contribute in different ways to the research project. It can be in kind, which is engineering time, batteries or whatever, or much funding, which means if they get money from the research council, the company will give a similar amount. That sort of thing.
So I can say this depends really of which project, because typically we have some applied project to improve or to make some development, and then we have cooperations with some university and some public, and then we can do both, or have a budget to finance the researcher, or have a joint work without R&D guys that can make time. So we have both. There is no, this depends really specifically from the project.
Thank you. So the next one is which battery model is mainly used for EVs? Will this specific battery model be suitable for fast charging of EVs in the future? I think this is related to your presentation, Renato.
Okay, I see that for EVs, we have a family of batteries which called the Z family, that are a certain number of batteries that are ranging, say, from 500, the high voltage are ranging from 500 volt to 650 volt. We have a complete family that is used in buses application and so on. With reference to the, so it is a family more, to give a general idea, the battery module is in the range from 21 to 25 kilowatt hour each, and then can be connected in parallel to get the right energy that is necessary to make the service, to design to make the service. For the fast charging is the same situation as explained before from Cara. So we are an energy battery. We are not very keen to the power. So and the fast charging is more something related to have high power batteries. So we can say, as I mentioned it before, we will have a quick charging. Probably will increase a bit, but I do not expect to have a big variation. So not from if we are now 1 hour, we can expect 10-20% of improve, but not to go to the 15 minutes fast charge.
Okay, thank you. We're hitting 5 o'clock in Cardiff. I guess it's not that late. We're in the US and Brazil, but I guess we need to stop at this point, and we'll address the remaining questions in writing if that is okay with you. And on a Friday afternoon, I'm sure most people would like to go and enjoy the weather before it starts raining. We expect a lot of raining in the UK today. So before I close this, I'd like to first of all thank you all three of you for excellent presentations, excellent patience with all the questions, and really nice answers, replies to all queries that we had. I really enjoyed this afternoon, and I hope we will have the opportunity in future to meet in person once all this situation is changed. So wasting too much time, I'd like to thank you so much for your contributions today.
Okay, bye-bye, thank you very much.
With this, we close the webinar today, and please look out for the emails to tell you about the presentations and the recorded webinar. Thank you all, and bye-bye.
Thank you very much.